In this video, we're going to take a look at the center of mass of thin plates, which we refer to as a lamina. So down here, we have a function, f of x, and so we have a region underneath that function bounded by a and b and the x-axis. That region R is what we refer to as the lamina. All right, it's a two-dimensional surface. We just assume that there's absolutely no thickness to it whatsoever. So if you were to think of that as some type of a plate, and you want to find the balancing point, you want to find the center of mass of that point that would balance. So if you were to take a thin object of this shape and you were to balance it on a pole or your finger or something, it would perfectly balance. That's what we're looking for. And so to do that, we're actually going to get into a little bit of calculus here. So remember that we discussed before that mass is equal to density times volume of something that has volume. Now, something like our lamina, which is only two-dimensional, then there's no thickness to it, then the mass is density times area. So we looked at that concept in some previous sections and some previous videos. So density times area. So to find the center of mass of the lamina, we want to find the total mass of the lamina, as well as the moments of the lamina with respect to the x and the y axes. So to do that, we're going to take the area underneath the curve, and we're going to break it into little rectangles, just like we always do. And so we want to find the mass of the little rectangle. So we want to find the mass of this rectangle. And so remember that mass is density times the area of the rectangle. And so density is usually a constant. It's given to us. And then we can find the area of the rectangle just by taking the length times the width. So the length of the rectangle is the function value, and the width of the rectangle is delta x. And so that gives us this right here. Density times f of x sub I times delta x. That gives us the mass of one of these little rectangles. Well, of course, we're going to create a whole bunch of little rectangles, and that creates a Riemann sum. And so then we are going to sum up all of the masses of those rectangles. And we get the total mass of the lamina. Then, if we want a more accurate result, what do? We, of course, take the limit as the number of rectangles approaches infinity, and that gives us an integral for mass. Mass is equal to the density times the integral from a to b of the function, f of x dx. So finding the mass is just a matter of integrating the function and multiplying it by the density. So the same thing is true in some of these problems that is true in one of the other sections we did, that the calculus isn't really all that difficult if you just kind of learn the basic procedure. Some of the theoretical development is very complicated. And as I did in some of the other videos, I'm going to be skipping a lot, especially right here. All right? The development of finding the moment about the x-axis is in the textbook. If you're interested in knowing exactly where this comes from, then go to the OpenStax textbook and read through that. You might find it very interesting. But for brevity and to make sure that this video wasn't 2 hours long, I decided to just kind of skip to the chase. Hopefully you appreciate that. So anyway, the moment about the x-axis is the limit as n approaches infinity, in other words, the number of rectangles approaches infinity, of the sum of density times the function squared divided by 2, delta x. So as an integral, we get this integral. Density times the integral from a to b of the function squared divided by 2. So that's not really that complicated, except sometimes squaring the function can be annoying. And then the moment about the y-axis, the limit of the Riemann sum of density times x times the function delta x, which as an integral gives us density times the integral from a to b of x times the function dx. So you do need to make sure that you keep these separate in your minds. So all three of these integrals, this one right here and these two down here, are somewhat similar. They all have density out in front. Density times the integral, density times the integral, density times the integral. This is just the integral of the function. This is the integral of the function squared divided by 2. This is the integral of the function times x. And again, if you want to know where these formulas come from, go to the book and take a look. Okay, then these formulas are basically the same. The actual coordinates of the center of mass, the x-coordinate, is the total moment about the y-axis divided by the total mass. And the y-coordinate of the center of mass is the total moment about the x-coordinate divided by the total mass. And so this box down here sums up all of our important relationships. There's your mass integral, and right here are your moment integrals, and then finding the center of mass. All right, let's do a problem. Oh, before we do a problem, I do want to mention something here. Yeah, be kind of useful. So when we're finding x bar, you'll notice that we're doing m sub y divided by m. And so notice that m sub y is rho times the integral of f of x dx. And then the mass is rho times the integral, and I know I'm leaving off the a and the b, of f of x dx. Well, guess what? The rho's cancel out. So when you're actually doing these calculations, you can disregard the densities because the densities are always going to cancel out. And the same thing, of course, is going to happen when you do the calculation for the y coordinate of the center of mass. You're going to have rho times f of x squared divided by 2 and rho times the integral of f of x dx, and the rho's are going to cancel out. So the density really doesn't figure into the calculation for the center of mass at all. All right, so now let's go to our first example. Let R be the region. I didn't label that. That would be here. R is this region. Underneath the function, f of x equals the square root of x, and above the x-axis, and between 0 and 4. So the first thing I like to do is find the mass. That's usually the simplest thing. Now I'm leaving rho in here. We don't know what rho is. They don't even give us a density, but we know that the density is going to cancel it anyway. But I just went through and I put rho in as an unknown density, and you're going to see that it cancels out. So here's my formula. And so we want rho times the integral from 0 to 4 of the square root of x dx. When we integrate that, x to the 1/2, that becomes x to 3/2 times 2/3. And so we get our mass is 16/3 times density. Then we want to find the total moment about the x-axis. And so that is this formula. I always like to write down the formulas just to kind of help me remember them. Total mass about the x-axis is rho times the integral from a to b of f of x squared divided by 2. And so the square root of x squared is x divided by 2. Finding the antiderivative of that, we get x squared over 4 times rho. Evaluating it, the moment about the x-axis is 4p. Then the moment about the y-axis That is x times f of x. So x times the square root of x is x to the 3/2, right? And so integrating that, we get x to the 5/2 times 2/5 times rho. Evaluating it, we get the moment about the y-axis, 64/5 p. And then finally, putting it all together, let's see, 16/3, yep. Putting it all together to find the x coordinate of the center of mass, we take m sub y divided by m. So that's the 64/5 p divided by the 16/3 p, rho. They cancel out. Simplifying the fraction, we get 12/5. The y coordinate of the center of mass is the moment about the x-axis divided by mass. So we get 4 rho divided by 16/3 rho, and that simplifies to 4/3. So our center of mass is 12/5, 3/4 as an ordered pair. So doing the calculus really isn't that difficult. You got a couple more formulas to remember. Just make sure that you develop an orderly process for how to go about doing these problems. All right. Now, I have to apologize for this one ahead of time. We don't know how to integrate everything in this problem. You will in the next chapter. So I just went through and did it for you, but at least you can see the process of doing one of these problems. Hopefully, there isn't one in the homework that slipped by me that has some integration techniques that we don't know yet. All right, so let R be the region bounded above by the graph of f of x equals e to the x and below by the x-axis. So I didn't draw a graph. If you needed to see a graph, you've got e to the x, something like this, and we're going from 0 to 4. And so you've got something that looks this region in here from 0 to 4. And we want to find the center of mass of that lamina. So the first thing that we do is we use our mass equation. And so that's the integral from 0 to 4 of e to the x dx. So the antiderivative of e to the x is e to the x. Evaluated from 4 to 0 is e to the 4th minus 1. So our mass, total mass, is e to the 4th minus 1. The total mass about the x-axis is the integral from 4 to 0 of e to the x squared divided by 2, or I multiplied it by 1/2 here. So e to the x squared is e to the 2x. I brought the 1/2 out in front. I always like to bring my constants out in front. And so we have e to the 2x. All right, so the antiderivative of e to the 2x is going to be e to the 2x divided by 2. So in case you're wondering where that, the antiderivative of e to the 2x is e to the 2x times 1/2. That's using u substitution, times this 1/2 gives me the 1/4. And so evaluating it from 4 to 0, we end up with this, e to the 8th minus 1 over 4. Now here's the part that we don't quite know how to do yet. We have to do something called integration by parts, which is section 1 of the next chapter. So that will be my next set of notes in my next video. So the moment about the y-axis is the integral of x times the function f of x, which is what we have there. And so we have to do this by something called integration by parts. And so I kind of go through some of what it's going to look like here, and we end up with this. Again, don't worry about how I got this for now. So 3e to the 4th plus 1. The important part is that you understand the process here. And so the x coordinate of the center of mass is m sub y divided by m. So that's going to be 3e to the 4th plus 1 divided by e to the 4th minus 1. The y coordinate of the center of mass is the sum of the moments about the x-axis divided by the sum of the masses, which is e to the 8th minus 1 over 4e to the 4th minus 1. Okay. So that's the process that you have to go through. I like to first find the total masses, find the total mass, then find the moment about the x-axis, find the moment about the y-axis, and then put it all together in your formulas here, and you're done. I believe that is it for this one. I am going to save the last two problems for video number 3. All right, see you then.